Okay, so let's have a look at this example here. We got a 25 horsepower motor uh, rotating at 1,750 RPM, and it's driving a machine with a multiple V-belt. These particular sizes of belts that we have a unit weight of 0.012 pounds per inch, and the V angle is 18 degrees. The pulley or the sheave on the driving side has a 3.7 pitch diameter, 3.7 inch pitch diameter, and wraps around such that we got 165 degrees of coverage there. So that's our phi. We're designing for a maximum belt tension of 150 pounds, and we can assume a coefficient of friction of 0.2. How many belts do we require? So first off, let's go ahead and calculate our PC here. So the tension due to centrifugal force. So first off, let's go for our V here. So our V, we're starting off with our rotational rate, 1,750 RPM. Divide that by 60 to give us our rotational rate in revolutions per second. So that is 29.1 rev per second. And then I'm going to multiply that by 2 pi to give us our rotational speed in radians per second. 183.3 radians per second. So if we want to get our linear speed, that's going to be that multiplied by a radius. So 3.7 inches divided by 2, because 3.7 was our diameter. So there we go. 339.1 inches per second is going to be our speed there. So got our weight distribution, and then unfortunately, because the imperial system is wonky, we need to take that and divide it by g. So 386 inches per second squared. For what it's worth, this is definitely, if you wanted to do this in metric instead, just convert everything and then do your calculations and convert back, I'm fine with that. But this value here squared. So again, units canceling out. I've got a per inch here, and another inch on the bottom. Sorry, per inch here. Got another inch on the bottom here, and then up here we got inches squared on the top. So those cancel out. Got a per second squared here, and we got per second squared here. Sorry, well, it moves up to the second squared moves up to the top when you divide it out. So that cancels out. We're left with pounds as our final result. So 0.012 divided by 386 times 339.1 squared. That'll give us 3.6 pounds. So we can go ahead and figure out what our tension ratios are. So again, P1 plus, P1 minus PC divided by P2 minus PC is going to be equal to E to the F phi over sine beta. So let's figure out what this term here is first. Our F was 1.2. The wrap was 165 degrees, but we want this in radians. So let's go ahead and convert that. So times pi over 180, and then all of it divided by sine of 18 degrees. 0.2 times 165 times pi divided by 180, and then divided by sine of 18 degrees. That gives us 1.864. So e to the power of that (6.45). And then so yeah, that's our maximum ratio here, taking into account the PCs as well. So again, P1 minus our PC. Well, okay, so if as for what P1 is, if our maximum belt tension is 150 pounds, then essentially we need to add our PC to our P1 to get that. So 150 minus 3.6, that gives us a P1 a maximum P1 of 146.4. So 146.4 minus 3.6 divided by P2 minus 3.6. So let's see here, that term on the top there. Let's rearrange this. So we got we can divide out we can multiply out this side and divide out this side, and that'll give us let's see, 142.8. That's this term up here, pounds divided by 6.45. That's going to be equal to P2 minus 3.6. So solving for P2, we get 25.7 pounds. So if we know what our P2 and our P1 is, then we can go ahead and figure out what our maximum torque. So again, the maximum torque that we can apply is the P1 minus the P2 times the radius. So 3.7 inches divided by 2, and I'm going to go ahead and also make this in terms of feet. So 1 foot per 12 inches. Inches cancels out, obviously. So what do we got here? So that leaves us with a maximum torque without slipping of 18.6 pound-feet. If we want to figure out what sort of work, we can transmit Wisp on that. That is torque times our rotational speed, again in radians per second. So 18.6 pound-feet times 183.3 radians per second. That's given us 3,409 pound-feet per second. And you'll recall that 1 horsepower is 550 pound-feet per second. So that is 6.199 horsepower. So we're trying to transmit 25 horsepower with that, so 25 divided by that. That gives us 4.03 belts that would be required in order to transmit the horsepower. So realistically, you know, you could probably get away with 4 belts. You know, compounding, rounding errors, and so on and so forth here. And again, depends upon how conservative this assumption that the belt tension is limited to 150 pounds is. But if not, you know, bumping it up to 5 belts, and you're definitely good to go. So yeah, there we go.